Hello everybody, and welcome to lecture 5 of our Calculus 1 course. So today we're going to talk about the second order derivative, and we'll briefly touch on higher order derivatives, third, fourth, fifth, so on. And the second derivative is going to do a few things for us, but also comes with a whole host of gifts in its own right. But a few things we're going to be focusing on is, well, one thing we have to focus on because this is a Calculus 1 course is maximums and minimums, but then also question of how a curve is curving, which has applications for improving approximations, and of course, as I said, maximums and minimums has implications for that, but also understanding what the graph of a function looks like. So let's start with sort of fundamental motivation for second derivatives. Let's say we have a curve and a tangent to a curve, which of course is how every conversation starts in calculus. You have a curve and you have a tangent to a curve. But now, let's say we have another tangent to the curve, and that we track the tangent to the curve over, as it's moving along. So you see that the tangent is getting less and less steep as we go along. And the slope of the tangent, so the curve is y equals f of x. And the slope of the tangent line is f prime of x, and the rate of change of the tangent line as we move along, the change of the slope of the tangent line is so rate of change of the slope is the derivative of the derivative, which is usually written 2 primes like that, double prime of x. And in this picture, the fact that the slope is getting less and less steep, that corresponds to f double prime of x is less than 0. The slope is decreasing. Now, of course, the slope is still positive, so in this picture, f prime of x is greater than 0, but f double prime of x is less than 0. So then I told you maxes and mins. So let's say we're just going along on a curve. Say this curve is increasing, it's going up, then eventually it reaches maximum and starts going down. So over here, as it's going up, the function is increasing. The function is increasing is another way of saying that the derivative is positive. The slope of the tangent line is positive, and then it eventually goes up, and it reaches its maximum point, at which point the tangent line is horizontal, and then it starts going down, and the slope becomes negative. So over here, f prime of x is greater than 0. It's increasing. And then let's call this point the maximum. Let's call the maximum x0. So we have the x-axis. So the x-axis, and let's call this point x0. So the maximum occurs at x0, and so f prime of x0 equals 0, right? It's a horizontal tangent. And then over here, on the right side, f prime of x is less than 0. So f prime of x is greater than 0 for x less than x0. F prime of x0 equals 0, and f prime of x is less than 0 for x to the right of x0, or x greater than x0. So a maximum occurs when the derivative is positive, and then it zeroes out and then becomes negative. So this is, for example, ensured when so picture again, we have x0 prime of x0, or f prime of x is greater than 0 over here, and then f prime of x is less than 0, x greater than x0. So this, for example, will be ensured when, so we have a max when f double prime of x, so, or rather I should say x0 is a max, x0 is a max when f double prime of x0 is less than 0. When one f prime of x0 equals 0, right, it's leveled out, and f double prime of x0 is less than 0. This ensures that there is a maximum. Now, the opposite statement, one could ask the opposite statement, are these things both going to be true at every maximum? Well, certainly this is going to be true at every maximum that f prime of x0 equals 0, right? Because if the slope is tilted at all, if it's not level, if the tangent line has any slope that's not 0, then it's still going somewhere. It hasn't reached a maximum yet. It's still going to be increasing more. You know, if it was negative, then it would be increasing going to the left. So that couldn't be a maximum. So certainly f prime of x0 has to be 0. So this will always hold for a maximum. But f double prime of x0 less than 0, does that necessarily have to hold? Well, we'll get back to that later. I like to think and talk about when things do work before getting into when they don't work. So let's explore this characterization a little bit. And a very natural place to explore it, I think, is with say f of x equals sine of x. That gives us a rich set of points to consider. So say f of x equals sine of x. So f prime of x equals cosine of x, right? And so let's do a little bit of a graph here. Negative 3 pi over 2, negative pi over 2, pi over 2, pi over 2, pi over 2. So just by looking at the graph of sine of x, you can immediately see that the maxes are, you know, at pi over 2, 5 pi over 2, you know, negative 3 pi over 2. But let's look at all the places where f prime of x equals 0. So this is where cosine of x equals 0. So cosine of x equals 0 everywhere where the slope of the tangent line is 0. Right, because the slope of the tangent line is cosine of x. And And this is going to be every multiple of 2 pi, or sorry, of pi over 2, every multiple of pi over 2, which is not a multiple of pi, because if the multiples of pi, that's slope is not going to be 0. It's going to be that's going to be where sine is 0, but it's going to be odd multiples of pi over 2. It's going to be pi over 2. I'll start from the right actually. Negative 3 pi over 2. Start from the left. And then right here, this one's flat at negative pi over 2. And then at pi over 2. And over here at 3 pi over 2. But if you notice, only these ones are maxes. The other ones are mins. So this is a max. This is a max. But these ones are actually minimums. And so let's apply the second derivative test. The second derivative test, f double prime of x equals negative sine of x. So that's very convenient. It's just the negative of the function sine x itself. So here, when the function is positive here, the second derivative, so this is sine of x equals 1 here, right? So the second derivative is going to equal negative sine of x, negative 1. And so f double prime of x, of pi over negative pi over 3 is less than 0. So that fits with our test for the maximum. But then down here, f double prime of x equals negative of negative 1, which is just going to be positive 1, so that's greater than 0. And that, you see, the slope is negative, and it's switching over now to being positive. And so that is the condition for a minimum, or that gives a minimum. That's the second derivative test for a minimum, is that the second derivative being greater than 0. So if the second derivative is greater than 0, then we have a minimum. So now, let me write some definitions here. So, have a curve, y equals f of x. So, x0 is a what we call a critical point. If f prime of x0 equals 0. So that's wherever there's a horizontal tangent. So in particular, all maximums and all minimums are critical points. So all maxes and mins, are critical points. Now you could ask, is the opposite true? Is the opposite true, that all critical points are maxes and mins? And so this is a definition. So you could ask, is the opposite true, that all maxes and mins, that all critical points are maxes and mins? And well, if you were to thoroughly think through all the functions you know, ask where are the critical points of this function, are they all maxes or mins, you would eventually stumble upon one for which there's a critical point which is not a max or a min, and that is x cubed, horizontal tangent line right here, critical point which is not a max or a min. Alternatively, if you didn't want to think through all the functions, and you just wanted to use your imagination to construct a case where this could happen, you could imagine like a saddle shape, think like the saddle of a horse, and you think, it gets steeper, and then it flattens out and then goes up. And then when you did that with your imagination, you'd be producing something that looks quite a bit like x cubed. And so x cubed. We could apply the second derivative test to x cubed to see what's going on. I mean, presumably we'll get 0, right? Because if the second derivative were greater than 0, then it would have to be a minimum. If the second derivative were less than 0, it would have to be a maximum. And sure enough, the second derivative of x cubed double prime equals 3x squared prime equals 6x. And you evaluate that as 0. That 0 equals 0. And that's where the critical point is. So the second derivative here is also 0. So let me just summarize our results about maxes and mins here too. So if f double prime of x0 is less than 0, and this is a critical, assuming x0 is a critical point, right? This is all under the heading of x0 being a critical point. If f double prime of x0 is less than 0, then x0 is a max, right? It's flat, and it's going from positive to negative, so that's a maximum. And if f double prime of x0 is greater than 0, x0 is a min. So this is called the second derivative test, as I may have already said. And you may wonder, well, what if f double prime of x0 equals 0, like we just saw with x cubed? Does that automatically mean it's a saddle point? It's not a maximum or a minimum? And I don't want to immediately give an example of that because it's disappointing when you see how something doesn't work. So let's look at some more examples of how it does work before we answer that question. So with the second derivative, so with the first derivative, everything is about lines, right? I mean, it's naturally everything's connected to lines, the tangent line. With the second derivative, the corresponding natural curve is a parabola. And we consider y equals x squared. This curve most certainly has a minimum, right? And f prime of 0 equals 0, right? Because f prime of x equals 2x. So the second derivative of f here is going to be just 2, right? That's the derivative of 2x. The derivative of 2x is 2. The second derivative of f of x is the derivative of the derivative. So f double prime of 0 is just going to be 2. So it's going to be positive. That's greater than 0. And that illustrates the fact that it's a minimum. The derivative is positive, and then it flattens out. It's negative. It's negative. The derivative is negative, and then it flattens out and becomes positive. So it's increasing. The derivative is increasing. Yeah. So, and then of course, if instead we had negative x squared, that would look like this, right? This being an x-axis, then we would have everything would be negated. Then f would be negative 2, and then we see we have a maximum. And yeah, so while we're on the subject of maxes and mins, I'll give you a quick example of when the second derivative test does not give us information. So let's say we have the function f of x equals x to the 4th. So we could ask, where are the critical points of this function? Well, f prime of x equals 4x cubed. Well, when is this 0? This equals 0 when? When does this equal 0? Well, this equals 0 obviously exactly when x equals 0, right? 4 times x cubed. If x is not equal to 0, this is not going to be 0. But if x is equal to 0, it is going to be 0. So the only critical point, is x equals 0. So then we ask, at this critical point, what happens with the second derivative? So, in this case, f double prime of x equals the derivative of f prime of x, right? So that's going to be 4 times 3, 12 times x squared. And so at x equals 0, f double prime of 0 equals 12 times 0 squared equals 0. So, and then you might say, well, okay, so it's a critical point, and the second derivative is 0, but if it was a max or a min, then the second derivative would either be positive or negative. But no, it doesn't work that way. It doesn't work that way. If the second derivative is positive or negative, it will be a max or a min, a min or a max, but it doesn't work the other way around, because here we actually do have a minimum. As you can see, if you draw the graph of x to the fourth, it's kind of like this, like a cup. We have a minimum right here at x equals 0. So it is a minimum, but the second derivative is 0. But then when we did with x cubed, the second derivative was 0 and we had a saddle. But now the second derivative is 0, but we still have a minimum. So if the second derivative is 0, then as far as maxes and mins are concerned, we don't have any information to go off of. That is not any information to go off of. I mean, we have other information like just drawing the graph. So the second derivative test will give us an answer if the second derivative is positive or negative, but if it's 0, it doesn't really tell us whether the critical point is a maximum or minimum. So before I move on to the next topic, the much anticipated topic, and further of better approximations and a further discussion of second derivatives, before we do that, let's do a quick story problem. So let's say that a farmer, usually in these story problems, there's usually a farmer. Farmer has 100 feet of fence, and he wants to enclose a rectangular region in this fence, with maximal area. So the perimeter, so 100 feet of fence, maximize, this is what the farmer wants to do. He wants to maximize the area enclosed by the fence in a rectangle. Okay. So we know that the perimeter of this fence is going to be 100. So let's call this the width. Let's call this the length. So the perimeter is going to be the 100. So 100 equals 2 times the width plus 2 times the length, right? 1 width, 1 length, 1 width, 1 length. So 2 times the width plus 2 times the length, 2 times the width plus the length. And so this tells us that the width, we could rearrange this, divide both sides by 2, so we have 50, divide both sides by 2, and then subtract L from both sides. So 50 minus L equals W. W equals 50 minus L. And so that tells us that the area, which equals the length times the width, equals 50 equals L times 50 minus L. Okay, so let's find the critical points of this function. Okay, so we want to find an optimal length and an optimal width. So, and this is of course is now just a function of length because the width is determined by the length. So a prime of L equals, take the derivative of this thing, and it's going to be 50 minus 2L, right? Because L times 50, derivative is going to be 50, and then this is just going to be negative L squared, so negative 2L. So, and this equals 0 when L equals 25. So great, so we know what length we need to have, and so the length is going to need to be 25, and then the width is going to need to be, remember, width equals 50 minus L, so that's going to be 25 as well. So that tells us that the optimal shape, the optimal rectangle to enclose the greatest area with this fence, this 100 feet of fencing, is going to be a square. Okay, so that's for the moment what I'll say about maxes and mins, and of course I'll give you lots of problems to work with maxes and mins because yeah, they're well, I'll give you one more example actually because you know, so that's a practical example, that's interesting, but I guess I should probably give you one more example just to try to increase your comfort level with this whole idea of maxes and mins. So let's say we have a polynomial x cubed minus 5x plus 1, and let's find where the maxes and mins are of this polynomial. So the critical points, so f of x equals this. So critical points are going to be when f prime of x equals 0, and f prime of x equals 3x squared minus 5. And so this is going to be when this equals 0 when x squared equals 5 divided by 3, which is going to be x equals plus or minus the square root, plus or minus the square root of 5/3. Okay, so this is the critical points. Then the second derivative, so second derivative test. Let's take the second derivative test. You can see that second derivative test for the critical points. So f double prime of x equals it equals the derivative of f prime of x, so the derivative of 3x squared, which is going to be 6x, and then 5 is just a constant, so the second derivative is just 6x. So then let's plug that in at the two critical points. So f double prime, can you see that? Maybe I will write it up. double prime equals 6x. Right. So I'll write over here. So f double prime of negative square root of 5/3 equals negative 6 times the square root of 5/3, which is of course negative. So this implies that negative 5/3 is a max. And similarly, f double prime of 5/3 is going to be positive. So also square root of 5/3 is going to be a min. So negative square root of 5/3 is a maximum. Positive square root of 5/3 is a minimum. And that shows us that the graph is going to have this N shape. So it's going to reach a maximum at x equals negative 5/3, and it's going to go back down and reach a minimum at x equals 5/3, and then it's going to keep going up. So this is interesting. It gives us a sense of the shape of the graph. So we don't even need to graph it with Desmos or anything, and we can already have this qualitative information that's going to have sort of an N shape. So that's pretty cool. It's a good mathematical skill, conceptual skill to be able to have. So now I'm really going to change the topic and start talking about other aspects of the second derivative. Well, it's interesting. So going back to our picture at the beginning. So we have a tangent line to the curve, and we consider what's happening with it a little bit later on. The slope is decreasing, so that this is a curve where f double prime of x is less than 0. The tangent line is decreasing. But another thing about this picture, is that the tangent line is always above the curve. And if you think about it, and I highly recommend doing a Desmos visual with pulling the tangent line around on the curve by moving the slider, x0 on the slider, is what you can see here is that the tangent line is always above the graph. And this corresponds to the fact that the slope of the tangent line is decreasing. Because as the slope of the tangent line decreases, the tail end of the tangent line is going to be sticking out above the graph, right? It's going to be pushed out away from the graph. But the graph is also going to be curving inward as the slope decreases, which means that the tangent line will be above the graph. And so the tangent line is the head of the tangent line will be above the graph. So that means that the entire tangent line, tangent line's above the graph, its entire tangent line's above the graph. All these tangent lines are above the graph, and that corresponds exactly to the second derivative being negative. And similarly, if the second derivative is positive, so the slope is increasing, and the tangent lines are always below the graph. So the second derivative of x is greater than 0. Tangent line is below the graph. The second derivative is less than 0, and the tangent line, the tangent line is above the graph. So then, a point where it crosses is called a, and let's make these x's x0 for consistency of notation, which is going to come next. So then when it switches, it's called an inflection point. So if f double prime of x, so if f double prime of x is less than 0 for x less than x0, and f double prime of x is greater than 0 for x greater than x0, then this corresponds to a switch. The tangent line switches. And you can see this, so f double prime of x is less than 0, so the tangent line is curving, the slope of the tangent line is decreasing on one side, and then, so let's say this is this point where it switches, and then now it's going to start increasing. The slope of the tangent line increases. The tangent line is above the graph, but then we get over here, and the tangent line starts being below the graph. So this point, so this is where it switches. So tangent line switches sides. And this would also be true if f prime of x was greater than 0 for x less than x0, and f double prime of x was less than 0 for greater than 0 for x. If we switch these, it would also be, the tangent lines would also switch sides, but it would just switch in opposite direction. And this is called an inflection point. Inflection point. Oh, sorry, it's a really awkward angle to write. Inflection point. It's called an inflection point. So an inflection point is where the tangent line switches from one side of the graph to the other side of the graph, and that can be mathematically, symbolically expressed by saying that the sign of the second derivative changes. Okay, so when we took the linear approximation yesterday, we had, a graph function giving us a curve, and say this is x0, f of x0. So here we have f of x, and this is f of x. This is the linear approximation. It's f of x0 plus y equals. So this is y equals f of x right here, and this is y equals f of x0 plus f prime of x0 times x minus x0. This is the linear approximation right here. So you see the problem, the reason that the linear approximation is not exactly right is that the graph is pulling away from the curve, the graph of y equals f of x, the curve is pulling away from the tangent line, it's pulling down. If you think about it, that corresponds to the slopes of the new tangent lines, their slopes decreasing. The slopes of the new tangent lines are decreasing. So in this picture, f double prime of x0 must be less than 0, right? And this is, so f double prime is called the curvature sometimes. It tells you how the function is curving. So it's pulling down, it's curving down when it's when f double prime of x0 is negative. The curve is pulling down from the tangent line, as opposed to if f double prime of x0 were positive, the curve would be pulling up from the tangent line, it'd be curving away from the tangent line. So the sign of the second derivative, the SIGN sign, positive or negative, the sign of the second derivative tells you whether the curve is pulling up from the tangent line or pulling down from the tangent line. Sign, it's frustrating that you would think there could be more different words that are unambiguously different. Sine, tangent, secant, we're using the same word to mean completely different things in all cases. But anyway, so this is where things get really cool. I mean, actually, they get really cool a lot of times in this class, but this is really interesting. This is where the second derivative gets really cool. So the second derivative, it tells you when the curve is pulling, when it's curving away from the tangent line. And so the sort of archetypal shapes for the archetypal shape for negative curvature is a upside down U, and or a parabola. So this kind of looks like the parabola negative x squared, which we know has negative curvature, right? It has curvature -2. So that's the second derivative of negative x squared is -2. And then the archetypal shape for positive curvature is just a U shape, more a sharper U, but a U shape, or which is like the graph of y equals f of x, or sorry, y equals x squared. So just upward opening parabola which has curvature 2. So and then you can see here, of course, anywhere you go on this curve, the slope is decreasing. Here it's positive and decreasing, and it's 0 and decreasing, then it's negative and decreasing, and here likewise it's negative and increasing, 0 and increasing, and then positive and increasing. The slope's always increasing. And so the terminology that sometimes is used is, in this case, it's called concave down. It's like a downward facing cave. And in this case, it's called concave up. Because it's like an upward facing cave, I guess. So that's the terminology I think we're going to use, is concave down, concave up. Sometimes this is referred to as convex, but then it gets confusing because different people use the different things to mean different things. But it's pretty unambiguous if you say concave down, concave up. Okay, so back to the linear approximation. So if instead of approximating with a line, we were to improve the approximation with a line by modifying the line with a parabola that moves in a little bit, replacing the line with a parabola that moves in a little bit, we get a slightly better approximation. And that's what the second order approximation really is that instead of approximating with a line, and this is not a good picture, it should be more like this. So it makes contact. Now we're gonna approximate with a parabola and get an even better approximation. And so this is called second order contact. So the tangent line, it has first order contact with the curve. It has the same first derivative. The slope of the tangent line is the same as the slope of the curve, and then here the curvature of this parabola is the same as the curvature of the curve, and so this parabola is said to make second order contact. Now, okay, so I'm telling you there's a parabola, but if we don't have a formula for the parabola, it does no good. Of course, what the formula is for this parabola is going to be the same as the linear approximation, only now we're going to add f. Can you see that blue? Is the blue visible? No, the blue's not very visible. So I would like to do it. I'll do it in orange. So this parabola will make orange. So plus second derivative of x0 over 2, and I'll tell you why it's over 2 in a second, times x minus x0 squared. Can you see that orange? Yeah. Okay, good. So the over 2 here comes from the principle of if it looks like a duck and it quacks like a duck, it must be a duck, or it must be closer to a duck than something that just looks like a duck but doesn't quack like a duck. So, and what I mean by that is that this parabola right here, its first derivative is So let's call this this parabola p of x, p for parabola. I'm going to write in yellow now because I'm really not sure if the orange is showing up good. So p of x is this parabola. So p prime of x equals, p prime of x0 equals f prime of x0, right? Because this is, now, okay, so this, let me take the derivative of the whole thing before I say that. So p prime of x, this is going to be a constant, and this right here is just going to be f prime of x0, right? And then this is going to be f double prime of x0 over 2 times, take the derivative of this right here, the derivative of this right here is going to be 2 times x minus x0, right? If we use the chain rule, the derivative of this is going to be 2 times x minus x0. So here 2 times x minus x0. And then of course these twos cancel, so it's just going to be f double prime of x0 times x minus x0. And then the second derivative is going to be just f double prime of x0. And so if we plug in at x0, what this tells us is that p prime of x0, plug x0 into this formula, and this term right here disappears, but we still have the f prime of x0, so p prime of x0 equals f prime of x0. So it looks like a duck, it looks like this curve, and p double prime of x0 equals f double prime of x0, so it quacks like a duck too. So it has the same first derivative, it has the same second derivative, so it has the same tangent line, it has the same curvature, and so it's a better approximation. Yeah. So let's apply this to an example, a concrete example, because right now this is all abstract. So let's look back to a question that I believe was on the last homework, sine of 1. Approximating sine of 1 from the base point x0 equals pi over 3. So on the homework, when you did this, you probably got it within two digits of the answer that if you put your approximation into the calculator and you put sine of 1 into the calculator, you probably got the first 2 digits the same. So I claim that what I'm going to show you now for the second order approximation, the first 4 digits are all going to be right, which is pretty good. So so x0 equals pi over 3, f of x equals sine x, so f prime of x equals cosine x, f double prime of x equals negative sine of x, right? Negative sine is the derivative of cosine. So sine of 1 is approximately equal to sine pi over 3. This is, f of x0 plus cosine of pi over 3 times pi over 3 minus 1. So this is the approximation that you probably would get on your homework, unless you approximate from pi over 4, which is also legitimate. But then with the quadratic term, and we have 1/2 of negative sine of pi over 3 multiplied times pi over 3 minus 1 squared. So then all of this, okay, so sine pi over 3, sine of pi over 3 is the square root of 3 over 2. And And cosine pi over 3 is 1/2 times, and then we multiply this times pi over 3 minus 1. So then again, this is probably what you got in homework, which would be accurate for the first two digits, but then we throw in this term, so it's going to be minus 1/2 of the square of 3 over 2 times pi over 3 minus 1 squared. This is going to be about 0.1, so this is going to be like 100th, and then this is going to be square root of 3 over 4, that's going to be less than 1, so this is going to be a really small correction. But this small correction gives us the next two digits. So let's try improving on our square root approximation, the square root of 65. So before we did a linear approximation of this, and we had square root of 64 plus 1 over 2 times square root of 64 times 65 minus 64. But now, okay, so because square root of x derivative is derivative of the square root of x is 1 over twice the square root of x, or 1/2 x to the minus 1/2. So then the second derivative of the square root of x is going to be negative 1/4 x to the negative 3/2, which in other words is negative 1 over 4 times the square root of x cubed. So in our second order, or we can call it quadratic approximation, or second order approximation, we add in 1/2 times the second derivative, which is going to be negative 1 over 4 times square root of 64 cubed, multiplied times 65 minus 64 squared. So this equals 8, this is the square root of 64, 8 plus 1/16. This is what we had before. And then plus 1/2 of, well, with the minus sign out, so minus 1/2 of 1/4, so we have 1/4 minus 1/8 over times 1/8 cubed. Of course, this is still just 1 squared is still 1. So this is going to be 1/8 to the 4th, so 1 over 8 to the 4th. And so you could type this into your calculator, type square root of 65 into your calculator, type this into your calculator, see if we're getting closer now. We should be getting closer. So yeah, so the second order approximation will get us closer, but then we can actually do what's called the third order, fourth order, fifth order approximation, and maybe the pattern, maybe it's apparent now, maybe it isn't. But so first we did is we had a curve, then linear approximation, you have a line that touches the curve, and then the next approximation is you would find a parabola that fits into this curve in some way. I should draw the parabola in a different color. It fits into this curve in some way. So that the curvature is the same for the parabola as for the curve, and then you get a slightly better approximation, right? It hugs the curve closer to the tangent line, but then you could do something with a cubic where it get even closer and closer, and this would be a third order approximation. So f of x, the linear approximation f of x equals x0 plus f prime of x0 times x minus x0 plus f double prime of x0 1/2 it's 1/2 of x double prime of x0 times x minus x0 squared. This is now the quadratic, sorry, this is approximate. This is the quadratic approximation. And then the third order approximation, we're going to have something involving the third derivative, which is the derivative, the second derivative. And what it is going to be 1 over 3 times 2 times f, third derivative. And why the 3 times 2? Well, what that is, sorry, this should be cubed, x minus x0 cubed. What that is when we take one derivative of this, we'll get a 3, one derivative, another derivative of this, we'll get a 2, and so this term right here, the third derivative of this term is going to be, as I said, it's going to be the second derivative of let's just take successive derivatives, so it's going to be the second derivative of 3 times x minus x0 squared, second derivative of this, right? And then the second derivative of this, if we take another derivative, it's going to be multiplied times 2 down here, so we're going to have 2 times 3. So this 2 times 3 cancels with the 2 times 3 over here, it sticks over here. And then we take another derivative, and we're just left with f triple prime of x0. And so this approximation now has the same third derivative as the initial curve. And so now it's going to hug the curve even more tightly than the quadratic approximation. It's going to be, it's the movement, its curving is going to be even better. And so it's going to approximate it even better. And of course, we could go on in this fashion indefinitely. We could then do plus 1 over 4 times 3 times 2 times fourth derivative of x0 times x minus x0 to the fourth. And now our approximations, they're going to start getting sharper here. And yeah, they're going to start getting sharper. And of course, we could just keep going and going and going, and the approximation would keep getting better and better. It'd be hugging the curve more tightly, more and more tightly. So let's use this to do something really bold, and let's try to approximate E. So E is e to the 1. So e to the 1, the linear approximation, this is approximately about 0, because 0 is a known value, right? We know that e to the 0 is 1. It's, explicitly computable without a calculator or anything. So this, it's a linear approximation. This is going to be approximately equal to e to the 0 times e to the 0 times, because e to the 0 is the derivative, right? But e to the 0 prime times 1 minus 0. So of course this just equals 1 plus 1 times 1. So it's 2, which of course we know that e is not actually 2. So that's not an incredibly good approximation. Now let's make it a quadratic approximation. And of course the second derivative, all derivatives of e to the x are just e to the x. So the second derivative is also going to be e to the x. So plus e to the 0 double prime over 2 times 1 minus 0 squared. This now, what we've done is, 1 squared is still just going to be 1. It's going to be 1 over 2. So this is going to be 2.5. Okay, well that's starting to look better. We know it's something like 2.78, so that's starting to look better. But then let's add plus e to the 0 triple prime over 2 times 3, or over 6, in other words, over 2 times 3, 6 times 1 minus 0 cubed. So this is going to be, 6 is like 1.6, or 0.16, 1/6 is like 0.16 repeating, right? If you put that in your calculator. So is that right? That yes, because 1/3 is 0.3 repeating, so 1/6 is 0.16 repeating. So this is going to be 1 plus another 1, 1 plus another 1 plus 1/2 plus 1/6, which is equal to 2.6 repeating. And so that's getting a little bit closer, and then by the time we did a fourth approximation, you would be able to tell that we're getting closer and closer. And if you look at this pattern, you can see that what's actually happening here is that it's just, if you think about the pattern, what's happening here is we're just doing 1 plus 1/2 plus 1/6 plus 1 times 2 over 3. Then the next one would immediately be 1, because everything, all the terms, when we're dealing with e to the 0, all the terms involved are going to be 1. This is going to be 1. This is going to, all the derivatives are going to be 1, and 1 minus 0 is going to be 1. So all that's going to matter is these coefficients right here. So this is going to be approximately equal to 2 times the sum of these things, and then 2 times 3 times 4, and then 2 times 3 times 4 times 5. And you can just keep going like this all day, and you can get arbitrarily good approximations of e to the x. So a similar method can be used to approximate sine and cosine with arbitrary precision, because we have cosine of 0. We know what cosine of 0 is, and we know that cosine prime of x equals minus sine x. So cosine double prime of x equals minus cosine of x, and then third derivative equals positive sine of x, and then the fourth derivative equals positive cosine of x again, and then it's just going to go back down the list, because we're just going to be taking more and more derivatives to the thing we already have. And the notation actually is usually, when you get past 3 or 4 derivatives, is you do a little number in parentheses instead of doing an absurd amount of apostrophes. So then this is going to be negative sine of x, and so the pattern at 0, the pattern is of course going to be, well, we're going to have cosine x itself. So the pattern is going to be 1 cosine x, and then cosine prime of x will be sine, it'll just be 0, and then here second derivative will be negative 1, third derivative will be 0, fourth derivative will be 1, fifth derivative will be 0, sixth derivative will be negative 1, seventh derivative 0 and 1, and it'll just keep going in this pattern. And so in the approximation about 1, what we'll have is, from this we'll get a 1, and then from this we'll get a plus 1/2, or plus 1/2 times minus 1 times x squared, so that's just minus 1/2 x squared, and then down here we'll get a plus 1 over 2 times 3 times 4 times x to the fourth. And then down here, we'll get minus 1 times 2 times 3 times 4 times 5 times 6 times x to the sixth. And then we'll keep going like this. And so if you do 1 minus 1/2 x squared plus 1/24 x to the fourth minus 1 over 720 times x to the sixth, then you'll already be seeing, well, I highly recommend doing this on Desmos. It's really cool. Like what you'll be seeing, so here you have with cosine you have this. And what you have is when you start, you just have 1. So 1 is right there. And then you subtract 1/2 x squared. And it comes down like this. You have a parabola that, drifts away after a time. And then once you add this in, it starts to touch the curve more. And then you subtract this, and it gets tighter and tighter into the curve, and you start seeing more and more of the sine curve, even as it moves around, which is really remarkable. I mean, it isn't going to work for every function under the sun, but it's going to work for a lot of the functions in this class, that when you do this type of approximation, it will become what's called a global approximation, where the entire curve, like with sine of x and e to the x and cosine of x, where the entire curve will be hugged by this by these higher order approximations. And so then when you have an expression like this in hand, then without your calculator you could approximate sine of 1, sine of 2, sine of anything. You could approximate with arbitrary precision, and you wouldn't even need to use foreknowledge of what pi is, or square root of 3, or anything like that we did with the previous example with sine of 1. So yeah, I mean, this is pretty good stuff. But I feel somewhat constrained as to how much I can focus on this in this class, because it's usually sort of a side topic in calculus courses, so it probably won't be over-tested. And so for the rest of this time, we still have quite a bit of time, or some time at least, and so I feel like it's my moral obligation to spend it doing the types of problems that are more likely to be tested on. So let's look at, and just as a brief side note, I mean, I was really hoping in this section to get up to approximating pi, but then I realized that it's not exactly easy to get to without a whole bunch of really obnoxious technical stuff, because like we've been doing with these things, we need to find arbitrarily high expressions for arbitrarily high derivatives of some function at some point from which we can approximate. And with pi over 4 equals arctangent of 1. So if we could approximate arctangent really, really well, arbitrarily well, then we could approximate pi over 4. And taking arbitrary derivatives of arctangent at 0 is not that hard, but it's just sort of would be an annoying thing to try to do in this class. It would take a lot of more explaining than I feel justified in doing, given the fact that this is usually a side topic in Calculus 1. But I'll tell you that the expression that you get for pi over 4 is 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 plus 1/13, on and on and on and on. Odd numbers alternating, 1 minus 1 over the next odd number, plus 1 over the next odd number, minus 1 over the next odd number, plus 1 over the next odd number, so on and so on and so on. But yeah, so I said I'd talk about stuff that's going to be tested on. So maxes and mins are usually regarded as being a very big deal because, optimization problems like the farmer and the fence. So let's do another max and min problem. So this conceptually is very similar to the last one we did, but without as much of a story, more concept, less story. So find the maximum value of the value xy subject to the constraint two x squared plus y squared equals 1. And if you think about it, there actually is a story to this one. And if you want to think about it, I'll just briefly say that the story to this one, xy, you can see that this immediately is a rectangle, but the story to this one is you have an ellipse, and the rectangle is inscribed in the ellipse. You need to find the maximum value of the rectangle. But anyways, that story aside, let's go ahead and do this problem. So this constraint gives us means for solving for y. So y is going to equal plus or minus the square root of 1 minus 2x squared. And then xy is going to equal plus or minus the square root, plus or minus x times the square root of 1 minus 2x squared. But of course areas are positive, so if we were going to do the ellipse interpretation, we would only really care about the positives. But of course, we're not doing the ellipse, but we are looking for the max value, so we only want the positives, because the negative certainly won't give us a max value. So the derivative of this is, we want to find where it's 0, right? So where does this equals 0 where? So product rule, this is 1 minus, the derivative is going to be 1 minus 2x squared plus x times, and then chain rule right here, we're going to have x times minus 2 times, that's the coefficient of this x squared, minus 2 times 2x all over the square root of 1 minus 2x squared. And this is going to equal, simplify it, 1 minus 1 over, so I'm going to replace this square root of 1 minus 2x squared as 1 over square root of 1 minus 2x squared times 1 minus 2x squared for the purposes of simplification. Then we can move in with this stuff. Oh, sorry, there's supposed to be a 2 right here because of the chain rule, and then these 2's cancel, so we get minus 2x squared. So all in all, we get 1 over the square root of 1 minus 2x squared times 1 minus 4x squared, which equals 0 exactly when x equals 1/2. Now, you might be thinking, well, how about we do the second derivative test or something to show that this is actually a maximum, and that would be a reasonable thing to do. But I'm going to leave it to you to do. If that is bothering you, I'm going to leave you to do it. Oftentimes in these optimization problems, it says find the maximum rather than find the critical points and show which one's a maximum. So you can save time by paying attention to the question that's being asked, because if there's only one critical point to be found and the problem says find a maximum, then you can assume, based on the information you've been given, that this will in fact be a maximum. So there is another maximum problem that's not in the graph form, but is in a different sort of representation of the function in question. We're not thinking of it as a graph, we're thinking of it as something else, an area or some abstract x and y multiplied times each other. But let's go back to another graph problem with find the critical points and classify them, say whether they're max or mins. So, and we'll further put this to a graphing problem where we'll incorporate the positive and negative curvature. So recall that when the curvature is positive, so when f double prime of x is greater than 0, we get this downward cup shape, and when f double prime of x is, this is when it's less than 0, and when it's greater than 0, we get an upward cup shape. This will help us in graphing a function. So the problem is going to be to come up with a freehand sort of sketch. This problem is going to be to sketch a graph of 1 minus x squared over 2 plus x to the 4th over 24. So this function, let's first find the critical points. So f prime of x equals 0 when, then take the derivative. F prime of x is going to be x, negative x, that is, negative x plus 1/6 of x cubed, and this can be factored as x times 1 minus 1/6 x squared. So this equals 0 when x equals 0 or plus or minus square root of 6. Right, because if this is plus or minus square root of 6, then this whole term is going to be 1, it'll be 1 minus 1. Okay, so let's make a little list of our known information. So x equals 0, or plus or minus the square root of 6. So critical points. X equals 0. Negative square, I'll write them in order. X equals negative square root of 6, 0 to the square root of 6. So now let's test which of these are maxes and which of these are mins with the second derivative test. In fact, let's just find some qualitative information about the second derivative in general. So, or rather some qualitative information about the graph by finding some quantitative information about the second derivative. So the second derivative equals, and I shouldn't have erased the derivative, it is going to be the derivative of the derivative, and the derivative was negative x plus x cubed over 6. So the derivative of this, so it's going to be negative 1 plus x squared over 3, right? X squared over 2. X squared over 2. And so this equals 0 when x equals plus or minus 1 over the square root of, when just equals plus or minus the square root of 2. So we can do a little number line. We have our critical points 0, and then negative square root of 6, and positive square root of 6. So then we're going to want negative square root of 2, positive square root of 2. And we also want to know where this is negative and where this is positive. So it's 0 at plus or minus the square root of 2. And then, so this is going to be positive when x squared is greater than 2, right? Because then this term will be greater than 1, and that will more than cancel the negative 1. So, and that's going to be when, this is square root of 2 negatives. So x squared is greater than 2 when x is either greater than the square root of 2 or less than negative square root of 2. So this is going to be, out here is where f double prime is positive, out here and out here. And then inside of here, f double prime is going to be negative. And so f double prime is positive at both of the critical points, both of these critical points, and negative at this critical point, which means that this critical point is going to be a maximum, and these critical points are going to be minima, and the function is going to be concave down around here, and going to be concave up outside, it's going to be concave down in here and concave up all around here. So we can graph this function then. So we have a maximum right here, and we're going to have minima around here somewhere, and it's going to be concave up. And we might wonder exactly how accurate is this picture, because what actually is f of the square root of 6, and we could just plug that straight in. So f of the square root of 6, or f of minus the square root of 6, f of the square root of 6, which apparently are going to be the same. So f of the square root of 6 equals 1 minus 6 over 2. So 1 minus 3 plus square root of 6 to the 4th, which is square root of 6 to the 4th is going to be 6 squared. So minus 3 plus 36 over 24. Of course, 36 over 24, divide both sides by 12, you get 3 halves. So this in total is going to be negative 2 plus 3 halves, which is just going to be negative 1 half. And so this value down here is negative 1 half. And I label this as negative 1 half too, because f of negative square root of x is going to be exactly the same thing, because in f it's going to be, this is going to be 6 and this is going to be 36, and it doesn't matter if x is negative square root of 6 or positive square root of 6. So that's that for lecture 5. We've covered second derivatives and several aspects of the second derivatives, the qualitative information we get from the quantitative information of the second derivative, and we've covered some approximation stuff. So I'm going to attach the homework worksheet and the test practice, and I'll see some of you in office hours tomorrow, or I guess it'll be today for for all of you when you watch this. And until next time.